Okay, so let's take a look at the two additional example for the chapter 30. Okay, so the first one. Okay, so here it says a long coaxial cable consists of two thin wall concentric conducting cylinders with radii A and B. Okay, so this is the inner one, and then this is the outer one. This is the outer one. Okay, so the inner cylinder carries a static current I, and the outer cylinder provides the return path for the current. Okay, the current set up a B field between the two cylinders. Calculate the energy stored in the B field for the length L of the cable. OK， 所以这个叫做 coaxial cable 的话，就是叫做同轴的线，同轴的缆线。通常用来传一些比较高频的讯号，因为它需要有一些电磁响应。它就是说，它就是两条同心的圆柱形。那信号从中间去的话，那外面那一层也可以当作地，但是它是一条 return path， 那这里叫做 return path， 它就是要有一些讯号去吐回来，让它，这个很难说，就是电磁学的话，后面会教，就是这门课不会教，就是比较，如果真的要学电磁学的话，会讲到一些叫做 transmission line，OK，transmission line 传输线，它就会跟那个负载的那个阻抗匹配有关啊，那如果阻抗匹配的话，全部信号都会传到那个负载上面去。那如果不匹配的话，有一些信号会反弹回来，那就是透过这个 return path 做到。OK， 所以它简单告诉你有这些东西，但是其实有一些很怎么说很困难的知识在背后的，但是我们目前的话其实还不需要知道这些。Okay, so here it asks you to calculate the energy stored in the B field. Okay. So first of all, we would like to apply the Ampere's law. Okay, integration of B dot ds equal mu 0 I. And actually the Amperean loop is, I suppose, is here, okay, with a radius R, okay, between the inner and outer cable. Okay, so here on the left side we have a B times 2 pi R, just as what we done before for many times, so I don't repeat why it look like that. Okay, so on the right side mu 0 I, okay, because there will be a current I here, okay, either going in or going out, it doesn't really matter, okay. It does not specify in this in the problem, so yeah, we don't care about that actually. So actually we have B equals mu 0 I over 2 pi R, okay, so a very familiar formula in chapter 29. Okay, so actually we need to derive the energy stored in the field for a length L. Okay, so in chapter 29 we also have a UB. This is a small UB. Okay, small UB equals B squared over 2 mu naught. Okay, so this is the energy density stored in the B field. So we can plug this one. Plug this one to here. So we can have mu 0 square and then cancel with 1. So we still have 1 there. Okay, and then I square, and then over this is 2 squared to be 4, and then this is another 2, so altogether we have 8, and then pi square out square. Okay, so this is the energy density. So dUB, okay, dUB, so this is a capital U, this is a capital U here, so which means it should be small ub times dV, okay, dV, this is the volume, okay, multiplied by the energy density, so that will be the energy, okay, for a specific radius. Okay, so which means we just plug in this one to here, so nothing special. So we have mu 0 I square over 8 pi square r square dV. Okay, and then we would like to make use of the cylindrical coordinate. So for the pelvis part, mu 0 I square, okay, 8 pi square r square doesn't change. And then for the dV, this is the cylindrical coordinate. Okay, this is not the spherical coordinate 啊，这个是圆柱坐标，因为它是一根 cable 嘛，所以它应该是圆柱坐标。So this dV should be RD theta and then dZ, okay, RD theta dZ. So you can consider dZ is an independent axis, and then these two R and theta, these two would be the polar coordinate, okay. So for the cylindrical coordinate, you can consider for the xy dimension, it becomes the polar coordinate, 极坐标, and then it is the independent, 一个独立的 z 轴就加在上面 ，OK， 所以就比那个 spherical 简单一些。spherical 的话，如果你还记得的话 ，spherical 的话是dV 等于r 平方 sin of theta dr d theta d phi OK， 如果你还记得的话，对，就是它就会有这个东西，因为第三个轴的话也跟前面两个轴有关系，它就是有两个角度在那里，所以它就会反正你看长度的 dimension 的话，dr 是一个维度，那这里有 r 平方，这里角度的话是没有 dimension 啊。那这里也类似啊，就是 dr 跟 dz 都是一个长度啊，所以这个 r 就是三维，那这个角度 d theta 就没有那个维度在。Okay, so this is the expression for dUB. Okay, so UB will be integration of dUB. Okay, so we can just isolate everything. Okay, mu 0 I square is a constant, and then over 8 pi square are also constant. So we just put all the constants in the front. Okay, it doesn't involve in the integration. So here we only have r square here, and then we have a r and then dr. So which means we have dr over r. Okay, so the range for this integration should be from a to b. Okay, because we need to integrate the B field between the inner and outer cable or the outer layer. Okay, so this is the dr part, and then for the d theta and dz. Okay, dz. Okay, so for the d theta part, it should be from 0 to 2 pi because it is a whole circle. So the theta should be somehow like this. Okay, this is the x-axis, and this is the x-axis. So when we pick a point here, okay, so this this one would be the theta. This one would be the theta, and then this one would be the r. Okay, so the r theta. Okay, something like that. Okay, so the theta will be starting from 0 to 2 pi to include the whole, somehow like the whole ring or the whole donut. Okay, for the dz, it tells you that the length is L. So it is nothing but 0 to L. Okay, so to make this one L, and then this is 2 pi, and then this is lateral log of B over A. Okay, so nothing special. So so this is nothing but mu 0 I square over. Okay, so we also have this L. We also have this L, and then for this 2 pi, these 2 pi partly cancel with this one. Okay, so it becomes 4 pi. Okay, so altogether we have a 4 pi, and then lateral log of B over A. Lateral log of B over A. So this is the expression for the UB between the coaxial cable within the length L. Okay, so for the question B, it is just ask you what is the stored energy per unit length of the cable if A, B, I take these values. Okay, so it just asks you UB over L. Okay, UB over L. So the energy per unit length. Okay, so the expression will be mu 0 I square over 4 pi, and then lateral log of B over A. And then we just need to plug in all the numbers. So mu 0 over 4 pi becomes 10 to negative 7. And then times I square is 2.7 square. And the natural log of B over A is 3.5 over 1.2. Okay, so this is 7.8 times 10 to negative 7. Okay, negative 7. Joule per meter. Joule per meter. Okay. So for the UB is the energy. So the SI unit should be joule, and then L is the length. Okay, SI unit should be meter. So J per meter. Okay, so this is the first one. We still have another. So this is additional example 2. So it says 2 parallel loops of wire have a common axis. The smaller loop radius r. Okay, so which means the top one. Okay, the smaller loop with radius small r is above the larger loop. Okay, so this is the larger loop by distance x. This is the distance. Okay, this is the distance. Okay, consequently, the B field due to the counterclockwise current I in the larger loop. Okay, so we have a counterclockwise current I for the larger loop is nearly uniform throughout the smaller loop. Okay, so because we suppose x is much larger than r. Okay, x is much larger than r. So which means this x is much larger than r, so that if it is far enough, so for this region, the B field generated by this current loop or the magnetic dipole we will consider the B field there is uniform. Okay, although it's not, there should be some variance， 就是这个 B field 在这个圆圈的区域里面其实是差一些的。我们之前有那个公式也是说，我们在这个 C 轴上面的 B field 但是我们会用到这个式子，那就是它就需要这个条件，就是说这个 x 远大于 r， 所以我们假设说这个圈 这个圈就会怎么说？这一点跟这一点的 B field 就会差不多啊，就会差不多。Okay, so so nearly uniform throughout the smaller loop. So suppose that x is increasing at the constant rate v equals dx dt. Okay, so you may suppose this is stationary, this doesn't move, and then this is moving upward. Okay, so there will be a constant rate or constant speed v equals dx dt. Okay, A, find an expression for the magnetic flux through the area of the smaller loop as a function of x. Okay, so we just assume the B field there is uniform. So that integration originally the magnetic flux should be integration of B dot dA, integration of B dot dA, but we just suppose all the B are uniform, pointing to the same direction, or we just assume it all the way pointing upward. Okay, so it turns out to be B times A. Okay, so for simplicity. Okay, so here we would like to make use of this one, 29, 24. Okay, but we need to slightly adjust the variable because at that time that is z-axis, but here this one is x-axis. Okay, so we need to make some tiny changes to the equation. So B should be mu CO2 pi, nothing special, and then times mu. Okay, so this is the magnetic dipole moment. Magnetic dipole moment will be n times I times A, NIA. N is number of turns, so there we have only one turn, so n equals 1. So it will be originally it should be n times I times A. Okay, so here n equals 1, and then I is do we have an I? Okay, so I, we just keep it a variable, so we have I times A. A would be the area, the cross section area. So for the circle is a pi r square. Okay, so this is mu, and then for the z, okay, as I mentioned, we would like to use x instead, so x cubed here. Okay, and then we also assume, okay, this is x-axis, so pointing to the I hat, okay, the unit vector of x. Okay, so if you are not sure, so you can also determine the direction of the B field here, whether it's pointing upward. So for the loop here, this is counterclockwise. So you use your forefinger for the direction of the current. Your thumb is pointing upward. So you know that the B field should be, at least at the center point is pointing upward. At the near point, okay, so maybe a little bit pointing the other direction, but close to pointing upward. Okay, so we already assume that the B field is uniform, which means we also assume that all the direction is pointing upward. Okay, for simplicity. Okay, so here phi B will be B times A, which is mu 0 over 2 pi, and then times I pi r square over x cubed. And then times A again, A is this area, so we multiply. So this one should be r square. Okay, so this one is the magnetic dipole moment. Okay, so should be from this one. Okay, Okay, so this one should be a capital R here. Okay, so I just make it like this. Okay, so that's R square. Okay, so and then and then for this for this A we count this one. Okay, so it should be pi small r square. Okay, so we just try to cancel something. Okay, so this pi and this pi cancel, so nothing else. Okay, this one becomes 2x cubed in the denominator, and then we have a pi, 1 pi, and then mu naught, and then I small r squared capital R squared. Okay, so this is 5b. This is 5b. Okay, so this is actually the expression of the magnetic flux through the area of the smaller loop as a function of x. Okay, so this is already the answer. This is already the answer. Okay, of course we will make use of it in the next question. Okay, so in the small loop, find B, an expression for the induced EMF and the direction of the induced current. Okay, so we just recall 5B is actually pi mu 0 I small r squared capital R squared over 2x cubed. Okay, so E will be negative d phi b dt. Okay, so this is the Faraday's law. This is the Faraday's law for this loop. Okay, for this loop. Okay, for this loop. Okay, so the phi b is actually here, and x is increasing. So this one, if we take the time derivative, okay, so it will be a non-zero value. Okay, so let's see what it is. So actually for most of the terms except this x cubed, okay, all the other terms are constant with respect to time. So we just need to put all those terms in the front. Okay, pi mu naught, and then I small r squared capital R squared over 2, and then we have a d dt, and then we have 1 over x cubed. Okay, like this. Okay, so this is so this x is a function of time. This is a function of time, so we need to apply the chain rule for this derivative. So negative pi mu 0 I small r squared capital R squared over 2. Okay, so this derivative, this is x to the negative third power, so the derivative becomes negative third over x to the fourth power. Okay, so this is the derivative. Okay, so this is like something so maybe we can, if you are not familiar with it enough, so you can consider this is a x, which is a function of time. So if we need to take dx, okay, so it will be dx dx, and then times dx dt something. So this is the chain rule. This is the chain rule. So this is x of so this is a function of actually a function of x, and actually it's a function of time. So you need to take the derivative with respect to x first. Okay, so which will write that, and then you also need to multiply it by dx dt. So this is due to the chain rule. Okay, so this one dx dt is actually v. So we can combine all the stuff. So we have two negative sign. Okay, so we have a negative sign here, negative sign here, so it becomes a positive sign, and so it will be 3 pi mu 0 I R squared capital R squared over 2x to the fourth power, and then also multiplied by v. Okay, so this is the expression for the EMF. This is the expression for the EMF. So this is the question for part B. And then for part C, what is the direction? What is the direction? So we know originally the B field is pointing upward, and then if x is increasing, we will expect this B is decreased, or the phi B should be decreasing. The phi B should be decreasing. So which means that the B induced should increase. The B induced should pointing upward to offset this change. So which means the I induced should also be counterclockwise. So the direction of the induced current, the direction of the IND is counterclockwise， 逆时钟就是说，因为这个圈在那边本来的 B field 是向上的，那如果它往上移动的话，你可以想象这个 B field 会变弱，因为离开原来这个current loop 更远嘛，所以它的 B field 肯定是更弱的更弱的。那更弱的话，那所以的话就是外来的这个 B field 减弱，也就是说它的磁通量减少所以它的 B induced 应该是往上往上。那用右手定着，你拇指向上，那 I induced 是逆时钟。Okay, so